Making sure we're doing the best we can to create as little waste as possible for both environmental and financial reasons is an important part of the job for many engineers. As chemical engineers, we work with a lot of reactions and solvents. With each reaction, there's our desired product and also byproduct and waste. Currently, engineers are designing a way to make azeotropes work in their favor to help with chemical waste minimization. An article we found discussed the Environmental Protection Agency and their policies for mitigating and reducing waste. These engineers suggested scientists may turn to purifying solvent waste at different pressures, but found this could impact the purity of their project. This is why they suggested using azeotropes. As we learned, azeotropes occur when the mole fraction of each species in the liquid phase equals that in the vapor phase. For example, if a mixture consists of species A and B, XA equals YA and XB equals YB. This can be used to determine characteristics of a solution when it is at the azeotrope, such as the composition of each species or the temperature and/or pressure at which the azeotrope occurs. To do so, it's best to start with the equations for fugacity in the liquid and vapor phases. Assuming that the system is in the liquid and vapor equilibrium, the fugacity in the liquid is equal to that of the gas phase, and from here, the equation can be simplified by setting xi equal to yi. Additional simplifications can be made based on particular conditions, such as whether the gas can be assumed to be ideal. Azeotropes can be represented in graphs too. This azeotrope diagram is considered a maximum boiling point azeotrope because the boiling point of the azeotrope is higher than the boiling point of any of its components. This is also called a negative azeotrope. Minimum boiling point azeotropes also exist, where the boiling point is lower than that of the boiling points of any other constituents. A plant in Taiwan used the properties of azeotropes to their advantage. They found themselves using IPA in two-phase column systems and getting ternary azeotrope water, IPA, and benzene. As a result, the scientists then performed azeotropic distillation on the azeotrope and were able to recover 4 tons of IPA daily with a very high purity rate, not only helping with the cost, but also productivity of the facility. Another cool example of this, with an interesting tie to our class, was a group of researchers who wanted to separate N-pentanol, cyclohexanone, and cyclohexene oxide, which are part of an oil, as a byproduct in the production of nylon. These chemical components all have similar boiling points, making it hard to distill and separate them. So for this reason, they tried using azeotropic distillation by adding water as an entrainer and then using an Aspen Plus to model what would happen. Their results found that using this method of distillation could help save 7% of annual costs. As 2 of us are working or have worked in the pharmaceutical industry for co-op, we've seen just how much solvent waste there is, and this is why it's important that engineers are developing solutions to manufactured waste so we can keep creating.